The next topic we're going to talk about is percent ionization. The degree of ionization of a weak electrolyte is the fraction of molecules that react with water to give ions. Basically, you're telling how much it ionizes. Electrical conductivity and some other colligative properties can be measured to determine the degree of ionization. So there's experiments we can do to determine how much something ionizes. However, when we're dealing with weak acids, it's fairly easy to do, okay, because simply all we have to do is measure the pH. Okay, with weak acids, the pH can be used to determine the equilibrium composition of the ions in the solution because it directly gives the concentration of hydronium ions at equilibrium. So, if I can measure the pH of a solution, I can determine how much hydronium ion is present, which then indirectly tells me how much it ionizes. Okay. Once I know the amount it ionizes, I can compare that to the amount of initial acid we had to start with, and that will give me my degree of ionization, percent ionization. So if I measure pH, it can give me my hydronium ion concentration at equilibrium, which then tells me how much is ionizing, that is that X that's being ionized. Compare that to my initial concentration of acid, and it will give me the degree of ionization, or percent ionization, as we're going to calculate in the next slide. To obtain the degree of ionization is the following calculation. Percent ionization is equal to the concentration of your hydronium ion at equilibrium divided by the initial concentration of the acid times 100%. Using our previous example, and the concentration of hydronium ion was 0.00041. If I divide that by the initial concentration of the acid, which was 0.012, multiply that by 100, I get 3.4%. Now, one thing to realize mathematically, okay, it's 0.00041 divided by 0.012 times 100. The percent, that's a unit, okay, just like grams, pounds, etc. It's just like a unit. So mathematically, it's 0.00041 divided by 0.012 times 100, and then you put the percent behind it as a unit. If you take 100 and hit the percent on your calculator, you're going to change that to 1, okay, which is not what you want to do mathematically. So mathematically, you multiply your fraction times 100, and you slap the percent sign behind it as a unit. So in this case, it's 3.4%. So there's not a lot of that acid being ionized, less than 5%, as I told you, for most weak species. Now, if I did the same calculation with a strong acid, what should happen is the concentration of that hydronium should be the same as the concentration of the initial acid, which should give me close to 100%. Weak acids typically ionize less than 5%. One thing to realize is the lower the percent ionization, the less hydronium ion being formed, which means the smaller the Ka, which in tail means a weaker acid. Okay, so the lower the percent ionized, the less hydronium being formed, the smaller the Ka, the weaker the acid. Realize that Ka is a measure of the acid strength. Okay, that size of K gives me an idea of how strong that acid is, okay, strength-wise, or Kb if it's a base. Strength is based on ionization, not the pH of the solution, okay? So strength is based on ionization by definition. The strength of an acid is based on how much it ionizes. The more it ionizes, the stronger the acid. pH doesn't directly tell me anything about strength. All a lower pH tells me is that it's more acidic. Okay, doesn't mean it's a stronger acid. Lower pH just means more acidic. Okay, so if I'm comparing pH to solutions, I can just say it's more acidic. I cannot say it's a stronger acid just based on pH. We talked about this before in the previous chapter, and I'm going to elaborate on it a little bit more on this next slide. Ka is the measure of the strength of an acid. Okay, it's a measure of the strength of an acid. It indicates the amount ionized to form hydronium ions. The more hydronium ions form, naturally the more acidic and lower the pH. However, when we're dealing with the strength of an acid, the term strength Okay, it is basically the measurement of the amount ionized. Okay, it has nothing to do with the concentration of the acid or how much or the pH of the solution. Okay, when we talk about strength of an acid, it's based on the measure of the amount ionized. Okay, concentration can vary, which ultimately will vary the pH of the solution. So to determine the strength of an acid, you must compare the Ka values, not the pH of the solution. pH is dependent on Ka as well as the concentration of solutions. So if I want to compare two acids to decide which one's stronger, then I got to compare apples and apples. Okay, here's an example. Got a 10 molar solution of acetic acid, has a pH of 1.87. Have a 0.1 molar solution of HF, has a pH of 2.08. I want to know which one of these is a stronger acid. Now we can go back to our relationships of polarity and size and make some decisions based on that to decide which one's a stronger acid, or we can use Ka to decide that as well. Now notice that acetic acid has a lower pH. That just means that it's more acidic. It does not mean that acetic acid is a stronger acid. What I need to do to decide if it's a stronger acid, I need to look at the Ka values. Okay, and I'm going to notice that the Ka of HF is larger than the Ka of acetic acid. So this has a larger Ka. Therefore, it means it ionizes more, which means it's the stronger acid. Now, just to show you that a little bit more, let's take these same two acids and change the concentrations. Now I'm talking about a 0.1 molarity solution of acetic acid and a 0.1 molarity solution of HF. Same concentration. Okay, so now I'm comparing apples and apples. Notice what happens to the pH. pH now is 2.87 for the acetic acid and 2.08 for the HF. You can see now that the HF is more acidic than the acetic acid. Now we're talking about the same concentration, so far they're ionizing. The one that ionizes the most will form more hydroniums, therefore have a lower pH. In the previous example, I had 10 molarity versus 0.1 molarity, so I was 100 times more concentrated on that acid than on the acetic acid than I was on the HF. And the pH is just a little bit more acidic. So you're going to compare apples and apples if I want to look at pH. So since these are both 0.1 molarity, then the one with the lower pH will be the stronger one because of the case that the ionization, the one that ionizes more, will have a lower pH. In comparison to the previous one, I was not comparing apples and apples. They were two different concentrations, so I couldn't just look at pH. All that pH told me was which one was more acidic. So ultimately, to decide which one's the stronger acid, I need to look at Ka. Okay, the larger the Ka, the stronger the acid. Okay, the larger the Ka, the stronger the acid. Okay, once we know the value of Ka, we can calculate the equilibrium concentrations of all the species involved, your acid, your conjugate base, and your hydronium ion. Or ultimately calculate the pH of a solution, which is what we're normally looking for. We want to know what is the pH of a solution, and ultimately that's what we're trying to do. The general method for doing this is the same way we've done Kc and Kp, with a simple change that we're going to simplify the math. Okay, remember back we said that the weak acids ionize a very little compared to the initial concentration. That's that 0.012 minus X equal 0.012. We're going to take this into account when we're doing calculations for Ka and Kb stuff. Something we didn't do when we did Kc and Kp, because those problems had Ks that were greater than 1. The Ks here are less than 1, so we're going to be able to simplify things. But we're going to have to look at it to make sure that we can do it, and we're going to talk about how we decide if I can eliminate that minus X or not. Okay, can I get rid of that minus X or not? Note that the previous example, the degree of ionization was very small as compared to the concentration of the acid. It was the small value of that degree of ionization that allowed us to ignore the subtracted X. in the denominator of our equilibrium expression to simplify that calculation. The degree of ionization of a weak acid depends on two things. One depends on the Ka, and it depends on the concentration of the acid solution. So if I'm going to neglect that X, if I'm going to say, 0.012 minus X is equal to 0.012, if I want to neglect that minus X, I got to look at the Ka value as well as the concentration to make the decision to say, yes, I can do that or not. So how do you know when you can simplify the assumption? How do I know that I can say 0.012 minus X is equal to 0.012? How do I know that I can say I can get rid of the X? What we're going to do is compare the concentration of your acid to the Ka. So I'll compare the concentration of my acid, divide that by my concentration of my Ka, and if it's greater than 100, then it's okay. I can neglect X. Okay, if my concentration of my acid is divided by my Ka is greater than 100, then I can neglect X. Ignoring the subtracted X gives an acceptable error of less than 5%. Now you may say, well, 5% is a pretty big number. Why is that acceptable? You got to realize that that's the concentration of my hydronium. That's a 5% error. pH is what we typically want. That's on a log scale, so that's 1/10 that error. So really, if I've got something with a 5% error in hydronium, that's only 0.5% error in my actual pH solution. That's pretty good. Okay, if I want it better than that, then get a pH meter and measure it. But if I want to just calculate it and get within 0.5% error, this is one way we can do it. Now, what if you do the calculation and you're less than 100? Then that means you have to do an exact calculation, which means you have to do the quadratic formula. Now, is there an easier way to decide if I can get rid of the X or not without having to do this calculation? Yes. Okay. Another way to look at it is look at the factor of if it's 2 or 3 difference in the powers of 10 between your Ka and the concentration. If you got 2 to 3 powers of 10 difference between your Ka and concentration of acid, you can neglect the X. Now, let's be on the safe side here. Okay, let's call it, instead of saying 2 to 3, let's go 3. Okay, if you got 3 powers of 10 difference between your Ka and concentration, you can go ahead and neglect the X. Okay, now what are we meaning by that? I'm looking at the powers of 10. I got some concentration to the power, say, -1, and some Ka, 10 to the -4. All I'm looking at is that power of 10 difference. And my 3 powers of 10 difference, -1 minus my -4, gives me 3 powers of 10 difference. Okay, if I'm 3 or more, I'm going to neglect it. No problem. Mathematically, it's got to work. Now, if it's 2 powers of difference, say it was -3 and -1, that's 2 powers of difference, it's questionable. It depends, if this 10 to the -1 is on the upper scale and the 10 to the -4 is on the bottom scale, that power 2 difference may or may not work. Okay, so the best thing is to calculate it. Okay, so if it's 2, then you should go ahead and do the calculation. If it's 3 powers of 10 or more, you're safe. You can go ahead and do your assumption. Let's look at an example. Calculate the pH in a 1 molar solution of nitrous acid for which the Ka is equal to 6.0 times 10 to the -4 at 25 degrees C. Okay, as I said, I want you to ask yourself some questions as you go through this. Okay, first question is this a single solute or is this a reaction? It's a single solute. That's an important question because eventually you will get into reactions, and all the calculation we're going to go to here, you're going to have to do this on top of something else. Okay, you would have to neutralize it before you get to this information that we're going to do right here. So the problems will continue to get harder and harder as we go, building on more information. The next question you should ask yourself is it an acid or a base or a salt? Once again, it's going to lead me to my next step to do. In this case, it's an acid. If it was a salt, there was more stuff we have to do. Okay, I'm going to have to look at the anions and the cations and decide if there's any acidic or basic properties and go on from there, which we haven't covered yet. We will. What I'm doing is laying the ground floor for you of how to do these calculations. I'm making them all look exactly the same. And you're just going to ask yourself different questions of where I go from here to get to the answer. Okay, the goal is pH of the solution. So we're going to have to just slowly get there by trying to ask ourselves questions, and then from those answers decide what I do next. Next question we're going to ask ourselves is it strong or weak, since it's an acid? If it's a strong acid, we know directly concentration of the acid gives us the concentration of hydronium. If it's a weak one, we know it doesn't. We're going to have to do hydrolysis, and we've got to do an ice table. Okay, so right there, once I know it's a weak acid, my next step is do my ice table. And in this case, nitrous acid, strong or weak? Weak. So what I want to do next is write my reaction. So I take my acid plus water. Once again, we're going by Bronsted-Lowry acid theory. We're going to take the proton and donate it from the acid to the base, which gets me hydronium ion and nitrite ions. Then I'll write my ice table. One more step I'm going to do before I ask which direction this is going to shift is that we have put in our initial of 1 and we put 0 for hydronium and 0 for nitrite. Well, I want you to realize that there is another equilibrium involved. We have your water-water solvent equilibrium. So it's not really 0. It's really something that got some contribution coming from that water-water equilibrium. So instead of calling it 0, I'm going to put an approximate sign there, meaning it's approximate 0. There is some coming from that water-water equilibrium, and I want to realize it's there because there are situations where that equilibrium may become important in our calculation when we're trying to decide the pH. Now, will that happen in this course? No, not going to happen, okay, except for one instance, which will come eventually. Okay, but for the most part, we're going to neglect that water-water equilibrium and concentrate only on the principal reaction. Anytime we're given any acid or base, we concentrate on the principal reaction and neglect the rest. But I want you to realize it's there, and I want you to realize how you can tell if you did need to calculate that water contribution. Okay, so right now I'm going to call it approximate 0, and I'm going to show you later how to tell if that was a good assumption or not. So next thing I got to worry about shift. So we know it's got to go to the right because I have no nitrate ion. Anything I got 0 on any side is going to have to point to that direction, which means then I've got to subtract my change in my acid and add my change for hydronium and nitrite. I need some relationship on the amount that it's ionizing. Don't know, so we call it X, which means I have X amount of acid being consumed and X amount of hydronium formed and X amount of nitrite formed. Add the two up to get my equilibrium, which is 1 minus X, X, and X. Then I need to take these three values and they're related somehow. How is 1 minus X, X, and X related? They're related through Ka. So now I'll set up my Ka expression, which would be my concentration of hydronium at equilibrium times my concentration of nitrate at equilibrium divided by my concentration of nitrous acid. Plug in my values at equilibrium, which are X, X, and 1 minus X, which gets me X squared over 1 minus X. Now I can do the quadratic formula and solve for this, or I can see if I can avoid that X and simplify the math. We said we do that by looking at the concentration of my acid to my Ka. If I do that, I get concentration of my acid divided by Ka. If it's greater than 100, I can neglect the X. In this case, it's 1 divided by 6 times 10 to the negative 4th, which is 1,667. Is that greater than 100? Yes. Therefore, what we're saying here, since this is the case, we're saying X must be much, much smaller than 1.00, which means then I can neglect the X. Now, could I have looked at this a little easier? Yes. 1, which is the same thing as saying 1 times 10 to the 0 power. Okay. times 10 to the 0 power. I can compare my powers of 10, and I can see there's 4 powers of 10 difference. We said if it's 3 or more difference, then it's okay to do the assumption. So just looking at the powers of 10, I could have came to the same conclusion and got rid of the x. That means then my math now changes into x squared over 1 is equal to 6.0 times 10 to the negative 4th. Multiply both sides by 1, which then gives me x squared is equal to 6.0 times 10 to the negative 4th. Where do I go from here? Well, I got an x squared term equal to some numeric constant. So therefore, I will just take the square root of both sides. And then that gives me my x, which is 0.024 molarity. Now, what you want to do at this point is ask yourself, what does x represent in this problem? Sometimes it'd be hydronium, sometimes it'd be hydroxide. You want to know what does it represent in this problem, which is why it's important to write the reaction. Write that reaction for you know how to solve the problem. Okay, in this case, we're saying it reflects the concentration of my hydronium ion concentration, but it also tells me the concentration of my nitrite ion at equilibrium. Not important to me in this particular problem, but it could be important to me somewhere in some other problem. But it's also giving me the nitrite concentration because of the fact that that's also equal to x at equilibrium. Okay. If I wanted the concentration of the acid, I would take 1 minus 0.024 to calculate it. Once again, don't care about that in this particular problem. My goal is pH. So now that I have my X value, which is the hydronium ion concentration, how do I figure out pH? Well, that's straightforward. That's your negative log of your hydronium ion concentration, which is the negative log of 0.024. Which sig fig wise, since I have 2 sig figs, it'd be 2 past the decimal, which is 1.61. Now I want you to ask yourself a question at this point. Does the answer make sense? Okay, does the answer make sense? Well, this is an acid, so what kind of pH should I have? Should be less than 7. Yes, that's what I have. So I have a chance of being correct. And that's very important because there are some careless mistakes that can happen right here. And if you ask yourself that question, you can go back and find where you made those careless mistakes. Where would those careless mistakes be? One would be the Ka. Okay, if you did this as a Ka problem and it was a base, then you had the wrong Ka, which would give you the opposite pH. When you ask yourself what does X equal, you may call it hydronium and it might be hydroxide, and that's where you would have the opposite, okay, and cause you problems as well. So that particular question is important because it gives you an idea, did you do the calculations correctly or not? Okay, so those careless mistakes where you flip-flop something can cause you to have pH on the opposite. And by asking yourself that question, you can catch those mistakes. Now remember, I said I had approximately 0, okay, for the hydronium ion because there is some coming from the water. Well, to decide if I can neglect that water, I go back and I look at the concentration of my hydronium ion. If that is greater than 10 to the minus 6, then I'm fine. Okay, if it's greater than 10 to the minus 6, which it is in this case, I'm fine on that assumption. I can assume that water is not contributing and I can move on. That's going to happen most of the time, okay, in this class. But I want to talk about it a little bit more, okay? We're going to do that on the next slide. Really, there's 2 equilibriums going on. You have your Kw, which is your water plus water, which most of the time we neglect. If the hydronium ion concentration is greater than 10 to the minus 6 from the acid by itself, which it was in this case. Really, the hydronium ion, the total hydronium ion concentration is equal to the concentration coming from the acid plus the concentration of hydronium coming from the water. Water is so small that we typically neglect it. But you got to realize there's what's going on here. You have one equilibrium. Which is your weak acid equilibrium, so it's forming hydronium ion and nitrite ions. But you also have your water equilibrium, which is contributing hydronium ions as well. The total amount of hydronium is a sum of both reactions, which means that your total hydronium ion concentration is equal to your hydronium ion concentration coming from the weak acid plus your hydronium ion concentration coming from the water. Now you might recall we did the water equilibrium by itself, and we found the concentration of the hydronium ion at equilibrium to be 1 times 10 to the negative 7 molarity, which is a very small number. Now you got to realize in that water-water equilibrium, if it's at equilibrium and now I'm adding some hydronium ion to it from that weak acid, well, what's going to happen to that equilibrium? Well, I'm adding additional hydronium, so it's going to have to relieve that stress. So it's going to consume up hydronium and shift to the left to produce more water, okay, because I added hydronium. It's at equilibrium. I added more of some of my products, so it's going to want to consume that, shift to the left to make more reactants to relieve that stress. Well, that means the amount of hydronium ion that is coming from that water-water equilibrium, that's going to go down because it's shifting to the left, which means then basically I'm getting less than 1 times 10 to the minus 7 molarity coming from the water-water equilibrium. So even smaller amount is contributing to the overall amount. So overall, I have 0.024 molarity coming from my acid. I have less than 1 times 10 to the minus 7 coming from the hydronium. Well, if I talk about sig figs and add these numbers, this is to the thousandths place, this is to the 10 to the minus 7th place. When I add that up significant figure-wise, I get 0.024 molarity, which means in essence, I'm neglecting the water contribution. Now, do I do that all the time? No. Okay. Will I do it all the time in this class? Just about all the time. Okay. As I said, there's one instance where it won't work, and that problem will come up soon. Okay. But for the majority of the time, we neglect the water. How do I tell that I can neglect the water? By looking at my concentration of my hydronium ion. If it's greater than 10 to the minus 6, we're okay. I can neglect that water contribution. Okay, let's look at another example. Calculate the pH of 10 milliliters of 1 molar solution of nitrous acid diluted to 100 milliliters with water, for which the Ka is 6.0 times 10 to the negative 4th at 25 degrees C. This is the exact same problem we just worked. Okay, 1 molar solution. However, we're taking 10 mils of that 1 molar and diluting it to 100. Remember, everything we're doing is based on concentration. So if I change the concentration, I'm going to change my amount of hydronium, which is going to change the pH. So you got to realize all these calculations we're doing, we always want to know what is the concentration after everything's finished. That's when we get to reactions. I'm going to have to figure out what's left to figure out the concentration to figure out what is the pH of the solution. So as I said, these problems are going to get longer and longer as we go. So let's look at this problem. Single solute, or is it a reaction? Not a reaction, it's a single solute. Next question. Acid, base, or salt? It's an acid. Next question. Strong or weak? Weak. That means I basically set up my ice table and go on with my calculation. Okay, once I get to that weak point. However, this one has a little bit more to do. I got to know what is the concentration. It's not 1 molarity. It's 10 milliliters of 1 molarity diluted to 100. So I'm going to have to do a calculation. That's typically your CV equals CV for dilution. Or in simple terms, you're just going to take your volume times molarity divided by total volume to figure out your concentration. So you got your volume times your molarity divided by your total volume, which is your CV equals CV just divided over, okay, by your total volume. Calculation, we have to do a lot. We got to know what is the concentration of it after it's been diluted, after it's been reacted. We got to know what is the concentration to do our calculation with our ice table. In this case, it's 1/10 concentration. Okay, it's 0.1 molarity. So that is the concentration I'm going to use in my ice table. Set up my ice table. I have my initial, my change in equilibrium. I got my initial 0.1, I got 0 hydronium, but I'm going to go ahead and add that little approximate sign because once again I'm assuming that water is negligible so I can get rid of it. And 0 for my nitrate. Since I only have since I have a 0 nitrate, this reaction has to go to the right. And you might notice that all our acid-base stuff is going to go to the right. That shouldn't be an issue for acid-base. KC, KP, yes, we had to figure out which way. Everything should be going to the right. So that means I got minuses on my acids and pluses on my product sides. I got to figure out how much it's going to change. Don't know. So I'm going to do a relationship of X, which is all 1 to 1, which means X acid's going to be consumed, X hydronium form, and X nitrite form. Add them up, gives me 0.1 minus X, X, and X. I now need some relationship between these three, which we say that in this case is going to be Ka. So I'll set up my Ka expression. Hydronium ion concentration times my nitrite concentration divided by my acid. Plug in my values at equilibrium, which is X, X, and 0.1 minus X, which gives me X squared over 0.1 minus X is equal to my 6.0 times 10 to the negative 4th. Do the quadratic formula, or I can make check to see if I can get rid of that minus X. That's your concentration of your acid divided by your Ka, which in this case is 0.1 divided by 6 times 10 to the negative 4th, which is equal to 167. Is that greater than 100? Yes. Therefore, we can neglect X. We're saying X is much smaller than 0.1, which means I can get rid of the minus X. Now, could I have done this a little quicker? Yes. 0.1 is the same thing as saying 1 times 10 to the negative 1. If I compare my 10 to the minus 1 to 10 to the minus 4th, that's how many powers of 10 difference? 3. And we said if it's 3 or more, we can neglect X. So therefore, we came up to the same conclusion and get rid of the X. That means now I have X squared over 0.1 is equal to 6.0 times 10 to the negative 4th. I now want to get X by itself, so now I'll multiply 0.1 to both sides, which now gives me X squared is equal to 0.1 times 6.0 times 10 to the negative 4th, which gets me 6.0 times 10 to the negative 5th. I want to get X by itself, so the next thing would be to take the square root of both sides, which then gives me my X value is equal to 7.7 times 10 to the negative 3rd molarity. I want to ask myself the question, what does X represent in this problem? In this problem, we're saying X represents the hydronium ion concentration at equilibrium. It also represents our nitrite ions at equilibrium. Once again, that's not something I care about in this problem. It may be something I care about in another problem, but in this problem, it doesn't matter to me. But it is important to me to realize what X represents in the term of hydronium or hydroxide. In this case, it's hydronium, which means calculating pH is equal to the negative log of that hydronium concentration, which is equal to the negative log of 7.7 times 10 to the negative 3rd. Since I got 2 sig figs, I have 2 digits past the decimal, which is 2.11. Notice that the pH is higher than it was last time. Why is it higher? Because it is now diluted. Okay, it's a diluted concentration of nitrous acid, which means my concentration's less, which means I have less hydronium, which means I'm going to have a higher pH. Once again, last question. Does the answer make sense? And the answer is yes. Okay, it makes sense. It's an acid pH and it's an acid. Now let's go ahead and check our little assumption. We said that if we can assume that water is not contributing a lot if we look at the concentration of my hydronium ion. Is that concentration greater than 10 to the minus 6 molarity? And the answer is yes. Okay, 10 to the minus 3rd is greater than 10 to the minus 6. Therefore, my assumption is okay. I can neglect the water. That's what we end up doing almost every problem, okay, in this course. That's not always in life. It's about this course. Now, you go to a higher chemistry quantitative analysis, you might not be able to do that. You're going to have to bring in the water. If you concentrate, and that's going to happen when the concentration of the acid gets really dilute. That's going to be a problem. But in this case, not a problem. And as I said, for most of the problems in this course shouldn't be a problem, with one exception being one that I'm going to do in lecture, which we eventually get to. All right, let's look at this problem. What is the pH at 25 degrees C of a 3.6 times 10 to the negative third molarity solution of acetylsalicylic acid, which is aspirin, which is HC9H7O4. Since I have one proton in the front, even though it has 8 protons, that's an indication this is a monoprotic acid. Ka is 3.3 times 10 to the negative fourth. Okay, so our goal is pH, which is most of what our goal is going to be on a lot of these questions in this chapter. Is basically what is the pH of the solution. So we're going to ask ourselves a couple of questions. First question, single solute or is it a reaction? Single solute. We haven't handled any reaction yet, but it's a single solute. Okay, if it's a reaction, then we have to do some calculations before we do what we're going to do in this problem. Okay. Next question, acid, base, or salt. If it's an acid, we're going to handle it one way, base, different way, one way, and then the salt's a different way. In this case, it's an acid. When it's an acid, the next question we ask ourselves, strong or weak? If it's strong, straightforward calculation. Weak, I got to do a Ka problem. In this case, it's weak. So since it's a weak acid, that's where I know I got to write my reaction, do my ice tables, and move on. So we write our reaction. Remember, Bronsted Lowry, you're going to donate a proton, form my hydronium, and form my conjugate base. Write out my ice table. I have my initial, which is 3.6 times 10 to the negative third. I have my approximate 0, and I have 0. Which way is it going to go? It's going to have to go to the right, which means I have minuses on my reactant sides and pluses on my product side. I need some relationship. I don't know how much it's going to ionize, so I'll call it X, which means it's going to be X amount of hydronium and X amount of conjugate base. Add the two up, gives me my equilibrium amounts, which is 3.6 times 10 to the minus third minus X. X and X. Next thing I need to ask myself is how are these three expressions related? And they're related through Ka. That's an important question because sometimes the answer may be Kb, maybe Ka1, Ka2, etc. So it's important to ask yourself how they're related. In this case, it's Ka. I need to set up my expression, which is hydronium ion concentration times my A minus concentration divided by HA. All that equilibrium, so I'll plug in those values. X, 3.6 times 10 to the negative third minus X, which comes to X squared over 3.6 times 10 to the minus third minus X is equal to 3.3 times 10 to the negative fourth. Now, I need to look at this and see if I can do my neglecting of X, which means I got to look at the concentration of my acid to my Ka and see if it's graded into 100. Okay, so I plug in my values. I get 3.6 times 10 to the negative third concentration of the acid divided by 3.3 times 10 to the negative fourth, which is my Ka, and I get 11. Is 11 greater than 100? The answer is no. Okay, which means I can't neglect the X. Okay, I can't neglect X. I'm going to have to solve the quadratic formula. Now, could I have done this calculation a little quicker without having to do concentration of acid over Ka? Yes, I told you to look at my powers of 10. And if you look at that, you can see it's only 1 power of 10 difference. We said that it has to be 3 or more power of 10s difference, which means you would also come to the same conclusion. No, I can't neglect X. Which is less than 100, okay, or it's not a factor of 3 or more difference for my powers of 10, therefore it won't work. Therefore, we must solve the equilibrium equation exactly, doing our quadratic formula. So we have our ice table set up. We now plug that into our expression, and now we now solve for our equation, trying to get everything on one side equal to 0. Okay, so in this case, I'll take the 3.6 times 10 to the negative third minus X, multiply that by both sides. And now it gets me X squared is equal to 3.6 times 10 to the minus third minus X times 3.3 times 10 to the negative fourth. Then I will distribute that 3.3 times 10 to the negative fourth through. So I'll multiply it times that negative 1, and also multiply it times that 3.6 times 10 to the negative third, which gets me X squared is equal to 1.2 times 10 to the negative 6 minus 3.3 times 10 to the negative fourth X. Okay, that 3.3 times 10 to the negative 4 is times that negative 1, which gets me that value of a negative 3.3 times 10 to the negative 4th x. And then I multiplied 3.3 times 10 to the negative 4th times 3.6 times 10 to the negative 3rd, which gets me 1.2 times 10 to the negative 6. Now I want to get everything to one side. I'm going to keep my x squared term positive. It just makes life easier. I could bring the x squared to the other side, but then I got a negative 1, which gets into places where I can make careless mistakes. So I want to keep as many things as possible positive as possible. So I will bring everything over to the other side, which means I will add I would add 3.3 times 10 to the negative 4th x to both sides, and I will subtract 1.2 times 10 to the minus 6 from both sides, which gets me the following: x squared plus 3.3 times 10 to the negative 4th x minus 1.2 times 10 to the minus 6 is equal to 0. I want everything equal to 0. That way I can set up my quadratic formula. The coefficient in front of x squared is understood 1, which is basically telling me a is equal to 1. B is equal to a positive 3.3 times 10 to the negative 4th. That's the term in front of x. And my C is equal to, that's with no term of x, a negative 1.2 times 10 to the negative 6. Okay, remember I got to bring the positives and negatives with it as well. So in essence, A is understood 1, B is 3.3 times 10 to the negative 4th, and C is a negative 1.2 times 10 to the negative 6. Plug that into the quadratic formula, which is a negative b plus or minus the square root of b squared minus 4ac. All of that divided by 2a. Plug in the values. Negative 3.3 times 10 to the negative 4th plus or minus the square root of 3.3 times 10 to the negative 4th squared minus 4 times 1 times a negative 1.2 times 10 to the negative 6. All of that divided by 2 times 1. I'm not going to show you the work here, but I will show you the two answers. So we do the first one. It'd be a negative 3.3 times 10 to the negative 4th plus the square root of the rest of the expression. I get an answer of 9.4 times 10 to the negative 4th molarity. That's your plus. I also have to do the minus, which would be a negative 3.3 times 10 to the negative 4th minus the square root of that expression divided by 2. And I get an answer there. My x minus is a negative 1.3 times 10 to the negative 3rd molarity. So we're going to get two answers. Which one's correct? One of them doesn't make sense. Okay, if I plug in the negative number, I'm going to end up consuming more than I started with. Okay, which that's not going to make sense. So therefore, the negative number is not correct. Now, will it always be the positive number? Yes, it would always be the positive number if you do the correct shift. If you wrote the correct shift, it's going to be the positive number. But what happens if you do the incorrect shift? Then it's going to be the negative number because you'd be doing a negative and negative. Okay, correct for that wrong shift. Now, should this really be an issue when we're dealing with acids and bases? No. Why not? Because everything's going to the right. Everything tends to go to the right because we got an acid, we put it in water, and then it goes to equilibrium and forms those ions. Okay, so everything's going to the right, so it should always be the positive number. That's not the case when we did Kc and Kp. Remember, it could go either way. Okay, so don't confuse that between the two chapters. So, next question is, what does X represent in this problem? Since I'm talking about an acid and I form hydronium ion, X represents hydronium ion. So, X equals hydronium ion, which is 9.4 times 10 to the negative 4th molarity. I want to calculate pH, so that's negative log of my hydronium, which is 3.03. Remember sig figs, 2 sig figs. I got 2 digits past the decimal. Need to ask myself, does this question make sense? Okay, got an acid. It's an acid pH. It's less than 7. Yes, it makes sense. As I said, that's an important question to ask yourself, because that's where you can see if you made some careless mistakes. Careless mistakes are going to be calling X hydronium and it's hydroxide, or hydroxide and it's hydronium. Wrong Ka. You used a Kb, etc. Those little things that you flip-flop is going to change the pH to the opposite. So asking yourself that question could save you some careless points on your final answer. Homework 29 deals with Ka questions. Okay, trying to solve for the pH of weak acids.